Left off on Wednesday's lecture where we're talking about two types of compounds, and I'll go ahead and put the two types of compounds up here. I usually put molecular compound on the left and ionic compound on the right. And you should have, if you've been kind of keeping up with what I was doing, kind of have tit for tat, kind of contrasting, compare and contrast information. What compounds have in common is that two or more different types of elements are stuck together with a chemical bond. We'll talk more about the nature of a chemical bond later. It is just such a beautiful sort of deal. So what I need to do now is talk about molecular weight. And I maybe already said this, but molecular weight is something that usually a lot of times students pick up right away. We know atomic weight by the periodic table. You definitely don't need to memorize the periodic table, but for every element, like we pick on potassium, 19 is the atomic number, now protons, 30.0983 actually serves two purposes. It's its average atomic weight in AMUs, and it's also its molar mass in grams per mole. So all we got to do is add up the individual weights of the atom in a formula. So we talked about two types of compounds, and we said the molecular compounds we call, I'm going to say the unit, I can't remember how I said it the other day, but 1 unit is equal to a molecule. And we said 1 unit for ionic compounds is equal to an FU, formula unit. So that tries to explain why you're going to see two slides. So if we have a molecular compound, we're going to talk about molecular weight. And if we have a ionic compound, we're going to talk about a formula weight. So here's what this looks like. Down here is the formula for aspirin. And notice it has 9 carbons. So we have 9. This 12.01 is the decimal number for carbon. It has 8 hydrogens, so we take 8 times 1.008, the decimal number for a hydrogen. We have 4 oxygens, the decimal number is 16.00, and then we go ahead and add those 3 numbers up. Okay, so we would say that a molecule of aspirin weighs 180.15 AMUs. Formula weights are done the same way, except we must be dealing with an ionic compound. So it looks like this, and we would call a formula weight, sometimes called a formula mass. So an example of an ionic compound that we could calculate the formula weight for would be sodium chloride. Of course, the other day I told you look for the metal, and sodium is a metal, so that makes it an ionic compound. Sodium chloride is just simply NaCl. So we have 1 sodium, and we have 1 chlorine. We add up to 2, and you're looking at a formula weight or formula mass of 58.44 AMUs. I like that crystal lattice structure. Digging that. Okay, so if you've got your stuff out, you can tell me if I go too fast. I don't have any whiteboards or anything, but we're going to knock out the molecular weight of hydrazine. So remember, the reason we call it molecular weight instead of formula weight is because it is a molecular compound. I said for all intents and purposes, we're going with hydrogens and non-metal. Now you can jot this down. Oh yeah, this is okay. So notice I'm taking 2 times how much nitrogen weighs, which is 14.01 AMUs, plus 4 times how much hydrogen weighs, which is 1.008 AMUs. On my calculator, I plug that in, and I'll probably get my calculator will display 3 decimals, but honestly, I'm limited to 2 decimals because of how much each nitrogen weighs. So simply, you would say that the molecular weight of hydrazine is 32.05 AMUs. So they're kind of fun. That's why I thought you guys will be fine for the Alta homework. But write it down, and I'll have to, maybe we should give extra credit like weekly?
Yeah.
Weekly? Okay. Well, the problem is the extra credit is only going to help your ALTA scores. The extra credit will help your ALTA scores so there's a way I can put an extra credit and I'll put it in a bucket. So it'll and if you've kind of maxed out your ALTA, then there's no place for it to go. But I will keep track of it, and if you miss any ALTA, I'll backfill. You know what I'm saying? Yeah. Yeah, and then, but I was thinking about extra credit points, and they have to be big because each one of your ALTA homework's worth 100 points. So they have to be big. Oh, and I didn't mention, somebody asked me a really good question. So you noticed whenever I give back a test, it's going to be usually a circle number. That's how many you got right out of, in this case, 64. And then I'll put the percentage. And it's the percentage that's going to show up in the grade book. So parts out of 100. So let me know if you have any questions. And I didn't necessarily curve it, but I did take it out of 60 and said 64.
Okay, so this isn't our overall kind of grade.
Though this percentage is the grade you got on this test.
Okay.
Yeah. So you can look in Canvas for your overall. Okay. So let's do another one. So we did this the other day. How many nitrogen atoms do we have here?
One.
2.
Why do we have 2?
Oh, because it's a line.
Yep.
Oh, wait, sorry. Yes.
Yeah, we have 2. Very good. In that same vein, how many oxygens do we have?
6.
Yeah. So here's how this one looks. So we're going to take 1 times calcium, which is 40.08 AMUs, plus 2 times nitrogen, because there's 2 nitrogen, so 2 times 14.01 AMUs, plus there's 6 oxygens, so 6 times 16.00 AMUs. And then the total, now this would be a formula weight, because it's an ionic compound. Talking about the repeating unit of a formula unit. And so the formula weight would be 164.10 AMUs. So don't be caught off guard. If your calculator displays 164.1, you're going to outthink your calculator and know that actually I've got 2 decimals in those 3 terms. Okay. So if this is an ionic compound, where's the metal there? Is it calcium, nitrogen, or oxygen? It is calcium. Yeah, calcium's the metal. It makes an ionic compound. So we're talking about. Did you have a question?
Now, why is it 1 for the first one?
Because there's just 1 calcium. Yeah.
Oh.
Yep. No, there's 1 calcium, and it's kind of like what we do in math, where we kind of nest things, and then outside the nest. So the things that is nested is the NO3, and that little subscript 2 means that quantity NO3 is times 2. Yes, 2 of those. Sir.
The second part, the 2 because of that one right there. It's calculating the NO, or
That's calculating the nitrogen and oxygen calculating.
so it's separate. It only applies to the nitrogen.
Yes.
It doesn't apply to the oxygen.
Right.
Okay.
Right.
Is it always going to be like that, or it applies? What's the rule of
The 6
the
applies
6
to
is
the oxygen.
the oxygen, yeah, because it's 2
And
times.
2 is the nitrogen.
It's always going to be like that. If we have a 2 on the outside, it's going to apply to.
Yes.
Okay.
Yep. Show your work. So we're not gonna get all the way through it, but I want to go ahead and start in on part 2. Okay. So, in Unit 1, we quite handily went from, I picked up potassium. In Unit 1, we quite handily went from how much potassium atom weighs to what's the molar mass of potassium. It was the same number. So quite handily for compounds now, you're going to see that we're going to go quite handily from how much a molecular formula unit weighs in AMUs to the molar mass of that compound. What is molar mass? We know that molar mass is the grams you need to set aside or weigh out in order to get 1 mole of that stuff. So units of molar mass are grams per mole. Grams of stuff per mole of, we've done it with atoms, and now we're going to do it with compounds. So these are examples of, I guess we call them compounds, I don't know. This is S8. This one right here, I was looking at it in my office. This guy is octanol. So it's this CH17OH. This red stuff, nasty. This is mercury 2 iodide, HgI2. This right here is methanol, CH3OH. And this guy right here is just a special form of sulfur. It's got 8 sulfurs in kind of this cool circle. But the point here is, remember the slides we looked at with regard to the elements, and you saw a beaker of an element, a beaker of an element, and the caption said all of those quantities are 1 mole. All of these quantities are 1 mole, in this case of molecules. I'm going to show you, all they did was basically weigh out in grams what the molecular weight is. Molar mass for atoms is equivalent to atomic weight. Molar mass for molecular compounds is the same number as molecular weight. And molar mass for ionic compounds is the same number as what you get for the formula weight. You just have to switch. That number that we just calculated does double duty. It does how much it weighs in AMUs, and also it's grams you need to measure out when you get 1 mole of that compound. Okay. So let's do a problem. This is nothing new. If you look at what the units of anything is, including molar mass, you know what you can use it as a bridge to use as a tool to go back and forth between. Units of molar mass are grams per moles, so we can go back and forth between grams and moles using that as a tool. So we did it for atoms, and now we're going to do it for compounds. So it's going to feel a little bit like deja vu, people. So on the previous part 1, we calculated the molecular weight and formula weight. Now I want you to calculate the molar mass. It's going to be like the same similar deal. I'm going to show you ethane. We're going to do it. We're going to do it explicitly, and then I'm going to show you an abbreviated way. So you can write this down if you want to, but I don't know. I'd wait till the next slide. This might give me hand cramp. There's an easier way that I do this. But explicitly, if the formula for ethane is C2H6, I need to account for the 2 carbons, and this is how I count for the 2 carbons. So for every mole of that compound, I have 2 moles of carbon, and I know from the periodic table that carbon has a molar mass of 12.01 grams per 1 mole of carbon. I need to take care of the hydrogen term. It looks like this. I can see I have 6 hydrogens, so I have 6 moles of hydrogen atoms in 1 mole of the compound. From the periodic table, I know that for hydrogen, it weighs 1.008 grams per 1 mole. I do the math. I come up with a number of 30.07. Again, we have to round it to 2 decimals because of this term right here. So you're going to go with 30.07, and units will be grams per mole. I know this is grams per mole of C2H6, but I would probably just say grams per mole. Instead of doing all that, that was explicit. I usually do it just like this. Isn't that better?
Oh, you can do that?
Okay.
Yes.
Okay.
So
Oh, I was like,
you
oh,
can always
yeah.
put grams per mole. You
Yeah.
don't even have to put C2H6.
Correct.
Okay.
She double checked. It depends on what sort of problem you're working with.
Okay.
Your question was, can we just go with grams per mole instead of grams of C2H6 per mole of C2H6? When we start doing problems that have 2 types of compounds or 2 types of substances, we have to be okay.
So this just like what we did.
This is just feels like what we did, exactly.
Just now.
It's what we did just now, but the units are different, right?
Yeah.
The units for molecular weight and formula weight are AMUs, and the units for molar mass are grams per mole.
Oh.
That's the only difference.
So like, would you count off if we didn't have any like labeling on the 2?
No. No, because that's how I do it, no. And you'll see, like, on my answer keys or whatever, when I do it, a lot of times I'll give it a heading, like I'll say, MM for me is molar mass. Molar mass C2H6, I'll do like a colon, and then I'll write it down. So that kind of labels it, but yeah, much better. Hand cramp. Right. Okay, so let's do another one, another compound. This is one of those, I said this the other day, there's no metal, but it's an ionic compound because ammonium, NH4, actually is NH4+, we call it polyatomic cation. But anyway, how many nitrogens do we need to account for? One. How many hydrogens? 4. Yep. Chlorines?
1.
Yep. So it looks like this. We have 1 times 14.01, and I usually do the 1, even though I know it's kind of redundant. Plus, you guys told me 4 times 1.008, plus 1 times chlorine's pretty heavy. 1 times 35.45. So how many decimals am I going to give this?
2.
Just 2, yep. Just 2. So you should get a value of 53.49, and then the units need to be grams per mole if it's molar mass, or AMUs if it's molecular weight. Okay. So I've been talking about the 2 decimals and all that for the problem we just worked, but here's the whole 3 decimals, 2 decimals, 5 decimals. In general, if you're dealing with something that's less than, that weighs less than 10, so boron, I'm looking at boron here, we got 10.81 for boron, but for beryllium, we got 9.012182. So it's less than 10, you go with 3 decimals in general. Okay?
Our table normally just have
The table, that black and white table just has 2. Okay.
2 or 3.
It has 3 at the top, right?
Yeah.
Yeah. Yep. Yep. So 2 for every 2 for things beginning with boron in general. And if you do that, then when you use a periodic table, it won't be your limiting. It won't be the one that makes you to round according to the data that you had and give you 4 sigmas. Okay. Well, that's a good place to stop. So we'll pick up here on.